The ground splits, buildings collapse, cities vanish in seconds, but not all earthquakes are the same. Some happen where plates collide. Others strike hundreds of miles deep where rock should be too hot to break. Some barely shake the ground but send walls of water across oceans. Hydraulic fracturing triggers tremors in places that never shook before. Magma moves and the earth screams. Which type kills the most? Which one hides in plain sight? What happens when the deepest earthquake ever recorded tears through rock at 457 miles down? If you value documented earthquake science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the United States Geological Survey's Earthquake Hazards Program with data published through November 2025, Geoscience World's peer-reviewed Geosphere journal with seismic research from 2018 and 2025, AOS, and Nature Communications with subduction zone earthquake modeling from March 2025. Now back to the information. Number 1, megathrust. May 24th, 2013, 609 kilometers beneath the Sea of Okhotsk. The Pacific Plate grinds under the Okhotsk Plate. Pressure builds for centuries. Then the fault rips. Moment magnitude 8.3. The largest deep earthquake ever measured. A 180-kilometer-long scar tears through the mantle. Rupture velocity 4 to 4.5 kilometers per second. Radiated energy 1.5 times 10 to the 17th joules, enough to power every home in the United States for 3 months. The seismic waves circle the globe 3 times. Buildings sway in Moscow. Skyscrapers in Tokyo record the shaking. But at the surface, nobody dies. Too deep. The energy dissipates before reaching populated areas. Compare that to the monster. December 26th, 2004, off the coast of Sumatra. The Indo-Australian plate shoves under the Eurasian plate. The Sunda megathrust, 30 kilometers deep, shallow enough to destroy. The fault locks for centuries. Strain accumulates, then 1,500 kilometers of coastline ruptures in 8 minutes. Moment magnitude 9.15, 15 meters of slip. The largest earthquake in 40 years, the seafloor jumps upward. Water displaces. A tsunami radiates across the Indian Ocean. Waves reach 15 meters in Aceh, 30 meters in some bays. 230,000 dead in 14 countries. The waves cross the entire ocean basin in 7 hours. Hit Somalia, Thailand, Sri Lanka, India. The Andaman Islands sink 1.5 meters. Entire coastlines vanish. Megathrust earthquakes occur where one plate dives beneath another. Convergent boundaries. The Pacific Ring of Fire. The contact between plates locks. Friction holds them together. The subducting plate keeps moving. Stress builds. Eventually the lock fails. The overriding plate snaps back. Elastic rebound. Massive energy release. Since 1900, every earthquake of magnitude 9 or larger has been a megathrust. The thrust fault that forms the contact can stretch 1,000 kilometers long. Dips at shallow angles. Less than 45 degrees. Huge displacement zones. The Cascadia subduction zone. From Cape Mendocino, California to Vancouver Island, the Juan de Fuca plate slides under North America. 600-kilometer fault. Capable of magnitude 9.3 according to United States Geological Survey assessments published in November 2024. The last time it ruptured was January 26th, 1700. The orphan tsunami. No written records in North America, but Japanese documents record waves with no local earthquake. Tree ring data confirms coastal forests drowned when the land dropped. Ghost forests. The recurrence interval is 300 to 600 years. We are overdue. The danger multiplies. Megathrusts generate splay faults, secondary ruptures that branch upward through the accretionary wedge. According to a USGS publication from November 2024, splay faults can create faster local tsunamis than the megathrust alone. The rupture happens in 2 stages. First, the megathrust slips. Then splay faults rupture at steep angles. 2 massive tsunami pulses arrive within minutes. The second wave often larger. Survivors of the first wave get hit by the second. No time to evacuate. The USGS estimates multiple splay faults within 30 kilometers of the deformation front in Cascadia could rupture simultaneously during the next event. Number 2, intraslab. Deep earthquakes within the subducting plate itself, not at the plate boundary. Inside the slab. February 13th, 2001. Nisqually, Washington. Magnitude 6.8, 47 kilometers deep. The Juan de Fuca plate bends as it descends. Internal stress fractures the plate from within. 400 injured, $3 billion damage, but the depth saves lives. A magnitude 6.8 at 10 kilometers would kill thousands. The mechanics differ. As the oceanic plate subducts, it cools, becomes denser than the surrounding mantle, starts to sink under its own weight. But The plate doesn't bend smoothly. Bending stress builds. The slab flexes. Faults develop within the plate. Extension on the outer bend. Compression on the inner surface. Eventually, the stress exceeds rock strength. The plate ruptures from inside. Interslab earthquakes radiate more seismic energy than interplate events of the same magnitude. A study from Geoscience World, published in August 2018, shows they have systematically higher stress drops. Regular earthquakes release stress immediately. Interslab events release it gradually, but with more total energy per unit area. Modified Mercalli intensity ratings run 2 points higher for intraslab quakes, compared to plate boundary events with identical magnitudes. Stronger shaking over wider areas. August 19th, 2018, 560 kilometers beneath Fiji, magnitude 8.2. The deepest magnitude 8 earthquake ever recorded outside of the 2013 Okhotsk event, a tie with the 1994 Bolivia earthquake at 630 kilometers, over 250 aftershocks in 34 days. Complex rupture on multiple faults. The Pacific plate subducts under the Australian plate. The slab reaches the mantle transition zone 670 kilometers down. Pressures exceed 200,000 times atmospheric. Rock should flow like putty, but it breaks. Why do deep earthquakes happen at all? 3 mechanisms compete: dehydration and brittlement. As the slab descends, water trapped in minerals gets squeezed out. Hydrous minerals like serpentine and amphibole break down. Release fluids, pore pressure spikes, reduces effective stress. Faulting becomes possible. Evidence comes from the geometry. Deep intraslab earthquakes align with subhorizontal faults, matching hydration patterns from outer rise, faulting before subduction. The amount of subducted water is 1 order of magnitude higher than previous estimates, according to research published in Nature in 2018. The faults that hydrated at the surface reactivate hundreds of kilometers down when dehydration occurs. Phase transformation. Olivine converts to spinel at depths of 400 to 600 kilometers. Same chemical composition, but 7% denser. The volume change creates microcracks. These cracks link up. Sudden shearing occurs. The 1994 Bolivia earthquake at 636 kilometers depth shows this signature. Thermal runaway. Shear deformation generates heat. Heat weakens the material. Weaker material deforms more easily. More deformation creates more heat. Positive feedback. The material suddenly fails along a narrow zone. Partial melting can occur at peak stress points. The deepest earthquake ever recorded, May 16, 2004, 735.8 kilometers beneath Vanuatu, magnitude 4.2. Below the mantle transition zone, the Tonga-Kermadec subduction zone produces the deepest earthquakes on Earth. The Pacific plate dives nearly vertically, sinks at 17 centimeters per year. Cold slab core preserves brittle behavior even at extreme depths. Over 75% of all deep focus earthquakes greater than 300 kilometers occur in this region, according to seismic catalogs from Wikipedia, updated in November 2024. Number 3, intraplate, within plate earthquakes, away from boundaries. The most mysterious type. December 16, 1811, New Madrid, Missouri, magnitude 7.5. The Mississippi River flows backward. Church bells ring in Boston. Ground waves visible to the naked eye. Chimneys collapse in Cincinnati. January 23rd, 1812, magnitude 7.4. February 7th, 1812, magnitude 7.5. 3 massive earthquakes in 8 weeks, smack in the middle of the North American plate. No plate boundary within 1,000 kilometers. Intraplate faults are ancient. Reactivated weaknesses in the continental crust. The New Madrid seismic zone follows a failed rift from 550 million years ago, when a supercontinent tried to split but stopped. The rift scars remain, buried faults that lost the tectonic lottery. Now they sit dormant, mostly. Stress from distant plate boundaries transmits through the continent. The North American plate pushes westward against the Pacific plate, compresses the entire continent. Ancient weak zones fail first. Earthquakes occur. January 26, 2001. Gujarat, India. Magnitude 7.7, 60 kilometers deep. Over 12,000 dead in Kutch district. Total deaths exceed 20,000. More than 400,000 structures destroyed. The earthquake struck over 300 kilometers from the nearest active plate boundary, pure intraplate. The Indian plate collides with the Eurasian plate along the Himalayas. Compressive stress radiates inward. Ancient faults within the plate reactivate. The Bhuj earthquake ruptured a previously unknown fault. September 3, 2016, Pawnee, Oklahoma, magnitude 5.8. The largest earthquake ever recorded in Oklahoma, 50 miles northwest of Oklahoma City. 6 kilometers deep, 12 people injured. Buildings damaged across 3 counties. This earthquake was induced. Human-caused, wastewater injection from oil and gas operations. Since 2009, Oklahoma has experienced a surge in seismicity. From an average of 1 to 2 earthquakes, magnitude 3 or greater per year historically, to over 900 in 2015, a 900-fold increase. The central United States went from 24 magnitude 3 or greater earthquakes per year between 1973 and 2008 to 688 in 2014 alone. Multiple damaging earthquakes. November 5, 2011, Prague, Oklahoma. Magnitude 5.7. February 13, 2016, Fairview, Oklahoma. Magnitude 5.1. November 7, 2016, Cushing, Oklahoma. Magnitude 5.0. The mechanism, oil and gas production, brings up brackish water with the petroleum. This produced water gets separated and injected into deep disposal wells. The Arbuckle Formation, a Cambrian Ordovician carbonate layer proximal to Precambrian basement. As wastewater fills the pores, pressure increases. Pressure diffuses deeper into basement rock, where most earthquakes occur. Faults that were stable for millions of years suddenly fail. Critical stress threshold crossed. Movement begins. Hydraulic fracturing plays a smaller role. In Oklahoma, 2% of earthquakes linked to fracking operations, according to USGS data current through 2018. The remaining 98% tie to wastewater disposal. Disposal wells operate for years, inject millions of barrels. Fracking happens in days or weeks, injects thousands of barrels. The volume matters, the duration matters. Between 2010 and 2016, 274 hydraulic fracturing wells in Oklahoma correlated spatiotemporally with seismicity bursts, according to a study published in the Journal of Geophysical Research in December 2018. About 700 earthquakes, magnitude 2 or greater, 12 events between magnitude 3 and 3.5. The scoop stack play accounts for most cases. The Arkoma Basin shows prominent activity. Studies published in 2024 by Scientific American report that even if wastewater injection stops, immediately earthquakes will continue for at least 6 years. Some models suggest 10 years or longer. The water is already in the ground, still diffusing, still increasing pressure. Oklahoma injected over 700 wells worth of wastewater stretching back 24 years. That water keeps migrating downward for years after pumps shut off. Number 4, volcanic earthquake, volcano tectonic. When magma moves, rock breaks. June 9th, 1991. Mount Pinatubo, Philippines. Earthquakes begin, swarms, hundreds per day. Magnitude 1 to 3. Shallow, less than 10 kilometers deep. Magma ascending. Pressure increases. Rock fractures to accommodate the intrusion. The earthquakes migrate upward as the magma rises. June 15th, 1991. The volcano explodes. Vi 6. 20 cubic kilometers of material ejected. 847 dead. Global temperatures drop 0.5 degrees Celsius for 2 years. Nearly every recorded volcanic eruption has been preceded by earthquake activity, according to a comprehensive study from Wikipedia, updated in August 2025. Volcano-tectonic earthquakes differ from regular tectonic earthquakes. They occur in swarms instead of main shock-aftershock sequences. Smaller maximum magnitudes, similar waveform patterns, increase before eruptions, occur near or beneath eruption sites. The movement of magma causes pressure changes. Surrounding rock must adjust. Brittle failure occurs. Seismic energy releases. 2 types exist. High-frequency volcano-tectonic earthquakes. Clear P and S wave arrivals caused by slip on faults near the volcano. The mass of the volcanic edifice adds to regional strain. Most have nothing to do with magma. They respond to regional stress in an area of weak faults, then low-frequency earthquakes, long-period events, vibrations from fluid movement, magma or gas moving through conduits, no clear phase arrivals, dominated by surface waves, harmonic tremor. Sustained vibrations, 0.5 to 5 Hertz. Continuous signal instead of discrete events. March 23, 2009, Redoubt Volcano, Alaska. Earthquakes occur at a rate of 30 events per second, so fast that individual events blur into tremor. Magnitudes 0.5 to 1.5. The earthquakes repeat, same location, same mechanism, stick-slip motion in the volcanic conduit, friction between magma and conduit walls, movement, stop, movement, stop, 30 times per second. The tremor precedes explosive eruptions by 30 seconds. The signal stops. Then the volcano blows. According to research published in Nature Geoscience in July 2013, this frictional faulting model explains the observations. May 26th, 2019. Hakone Volcano, Japan. Harmonic tremor originates at 30 kilometers depth. Lower crust. The signal lasts 10 minutes. Detected at stations 90 kilometers away. Apparent velocity 5 kilometers per second, matching S-wave velocity in the lower crust. Julian's flow-induced oscillation model from 1994 explains the mechanism. Magma, or supercritical fluid, flows through an elastic channel. The flow excites non-linear oscillations. The channel walls vibrate. Seismic waves radiate. Both magma and supercritical fluids can generate realistic tremor with channel dimensions of meters long and centimeters wide, according to studies published in Earth, Planets, and Space in July 2023. Number 5. Episodic, tremor, and slip. Slow earthquakes. Silent earthquakes. The newest discovery. 2001. British Columbia. GPS stations record unexpected movement. The North American plate shifts 2 centimeters southwest over several weeks. A 50 by 300 kilometer area. 35 days duration. No significant seismic signal. Energy equivalent to magnitude 6 to 7, but released so slowly nobody feels it. Aseismic slip. Researchers analyze GPS records. The events repeat. 13 to 16 month intervals. Last 2 to 4 weeks at any station. Then geophysicists extract the seismic signature. Low amplitude tremor accompanies the slip. Episodic tremor and slip. ETS. The Cascadia subduction zone. Juan de Fuca plate subducts under North America. The shallow zone is locked. Accumulated strain for 300 years, since 1700. Deeper down in the transition zone at 30 to 45 kilometers depth, ETS occurs. The plate boundary slips slowly. About 2 weeks of tremor and slip, magnitude equivalent to 7, but over weeks instead of seconds, tremor frequency 1 to 10 hertz. 2 week for standard seismometers, but dense networks detect it. The slip propagates along strike. Migration velocities 10 kilometers per day. Much slower than earthquake rupture, but faster than plate motion. The mechanism involves fluids. As the subducting plate descends, it releases water. Dehydration of minerals. Supercritical fluids form at the plate interface. High pressure, high temperature. These fluids lubricate the fault, reduce friction, allow slow slip. The fluids migrate, open fractures in surrounding rock. Tremor represents this fracturing process. Mathematical models, published in multiple studies through 2025, successfully reproduce ETS periodicity in Cascadia by incorporating fluid effects. March 11/20/25. Research published in AGU Advances shows tremor occurs first during ETS initiation. Slow slip acceleration follows 1 day later. The delay indicates tremor patches act as high-strength pins on the interface. They resist slip. The slow slip event can only grow after these patches rupture. Unpinning the interface, GPS data stacked from multiple stations reveals the timing. Geodetic moment accelerates dramatically about 1 day after tremor onset. The collective failure of critically stressed tremor patches enables major ETS events to emerge, very low-frequency earthquakes. VLFEs, part of the slow earthquake family, reverse faulting events, 5 to 20-second bursts, smaller than low-frequency earthquakes. Both magma and ocean bottom seismometer networks detect them. They track slow slip, even when tremor does not. During the 2011 ETS event in Cascadia, VLFEs show spatial and temporal correlation with GPS-measured slip. The matched filter technique identifies individual VLFEs. They continue throughout the inter-ETS period. Sustained activity above background between major events. Some inter-ETS periods show significantly elevated VLFE rates. Failed ETS initiations, local unpinning without enough critically stressed patches to trigger slip tremor feedback growth. Japan, the Nankai Trough, Southwest Japan subduction zone. ETS recurs at the plate boundary 15 to 40 kilometers deep. Similar to Cascadia, Mexico, the Middle America Trench. Slow slip events occur, but tremor patterns differ, not always coincident. New Zealand, Hikurangi subduction zone. Episodic slip with distinct reverse faulted micro-earthquakes instead of tremor. San Andreas Fault, non-volcanic tremor detected at transform boundaries, triggered by distant earthquakes. Number 6, tsunami earthquake. June 15/18/96, Senriku, Japan. Evening. Communities celebrate a Shinto holiday. Soldiers return from the First Sino-Japanese War. Magnitude 7.2, weak ground shaking. Most people don't notice. 30 minutes later, tsunami. Waves reach 38 meters, 22,000 dead, entire villages erased. The earthquake happened offshore. Shallow, top of the subducting Pacific plate, 20-degree dipping fault, 10 meters of displacement. But the rupture velocity was extraordinarily slow, under 2 kilometers per second, deficient in high frequencies. The slow rupture doesn't generate strong shaking. Humans don't feel it, but massive seafloor displacement occurs. Thick sediment in the accretionary wedge amplifies uplift. Efficient tsunami generation. Low seismic radiation. April 1st, 1946. Aleutian Islands. Magnitude 7.4 conventional. But the tsunami was catastrophic. Lighthouse keeper killed at Scotch Cap, Alaska. Wave height 30 meters. The tsunami propagates across the Pacific. Hits Hilo, Hawaii 5 hours later. Waves 10 to 15 meters. 173 dead. The earthquake ruptured 181 kilometers along the trench. Bilateral rupture. But energy to moment ratio, the lowest ever measured according to research published in Geophysical Journal International in June 2006. Theta equals negative 7.3. Extremely deficient rupture. Slip estimates range from 6 to 9 meters. Slow rupture velocity. Mechanically deficient media. Sedimentary wedge involvement. Tsunami earthquakes share characteristics. Surface wave magnitude much lower than moment magnitude. Body wave magnitude depleted. Source duration exceptionally long. 100 seconds or more compared to 10 seconds for ordinary earthquakes. Rupture at the shallowest megathrust. 0 to 15 kilometers depth. Large slip but slow progression. Inelastic wedge deformation. According to research published in Journal of Geophysical Research in October 2025, plastic dissipation in thick sediment generates moment-scaled radiated energy 10 times lower than regular earthquakes. The short wavelength seafloor uplift exceeds 5 meters, several times larger than elastic dislocation models predict. Impulsive tsunami with severe coastal impact. September 2, 1992. Nicaragua, magnitude 5.3 body wave, 7.6 moment magnitude. The discrepancy triggers investigation. The earthquake was barely felt. Coastal communities received no natural warning. Then tsunami, waves over 10 meters, 170 dead. July 17, 2006. Java, Indonesia, magnitude 7.7 surface. Source duration 185 seconds. Tsunami, 700 dead. October 25, 2010. Mentawai, Indonesia, magnitude 7.8. Tsunami earthquake, 400 dead. The shallowest megathrust ruptures pose unique hazards. Weak shaking provides no warning. Local populations unaware. Tsunami arrives in minutes. Number 7. Deep focus earthquake. Beyond 300 kilometers. The lower limit where brittle failure should be impossible. But earthquakes occur at depths exceeding 700 kilometers. May 24, 2013. Sea of Okhotsk. 609 kilometers. Magnitude 8.3. The record holder for the strongest deep earthquake. 180 kilometers of fault rupture. In the mantle transition zone, temperatures exceed 1,000 degrees Celsius. Pressure, 230,000 atmospheres. Under these conditions, rock should deform plastically, flow like taffy. No brittle failure. Yet the earthquake happens. The mystery persists. 3 competing mechanisms. Transformational faulting. Metastable olivine preserved in cold, subducting slabs. The slab sinks faster than it can thermally equilibrate. Stays colder than surrounding mantle. Olivine persists past its stability field. Pressure eventually forces transformation to spinel. The phase change occurs suddenly. Volume decreases 7%, density increases. The transformation creates a thin, weak layer. Microcracks form, linked together. Runaway shear instability. Laboratory experiments by Shubnal published in Science show acoustic emission events resembling earthquakes when olivine transforms under stress. Dehydration, embrittlement at depth. According to research published in Frontiers in Earth Science in June 2021, water subducts deeper than previously thought. Outer rise, normal faulting hydrates the oceanic lithosphere before subduction. That water travels down with the slab. At transition zone depths, final dehydration reactions occur. Fluid release, embrittlement. The 2013 Okhotsk earthquake shows sub-horizontal fault plane geometry, matching conjugate fault patterns associated with deep dehydration. Seismic tomography reveals low-velocity zones in the Okhotsk slab, indicating fluid presence. Thermal runaway. Plastic deformation generates heat. The heat weakens surrounding material. Weaker material shears more easily. More shearing produces more heat. Positive feedback loop. Temperatures spike locally. Partial melting possible. The material suddenly fails catastrophically. Stress drops in deep earthquakes exceed those in shallow events. The 2013 Okhotsk earthquake had stress drop 12 to 15 megapascals. An aftershock in the same sequence showed stress drop 1 to 2 orders of magnitude higher. Massive stress heterogeneity within the deep slab. August 19th and September 6th, 2018. Fiji, deep earthquake doublet. Magnitude 8.2 at 600 kilometers. Magnitude 7.9 at 670 kilometers. 18 days apart, both normal faulting within the subducting Pacific Plate. The first event ruptured 102 to 152 kilometers. Fast rupture velocity 4.1 kilometers per second. The second event slower, 2.5 kilometers per second. Complex slip, strike slip, and dip slip components. Over 250 aftershocks in 34 days after the first event. Coulomb stress transfer from the first earthquake may have triggered the second. But 18 days is long for triggered events. Dynamic triggering possible, but unusual timescale. The geographic distribution matters. The Tonga-Kermadec-Fiji arc accounts for 75% of cataloged deep earthquakes, but none of the 10 largest in the last century until 2018. The cold slab temperature allows brittle behavior at depth. But the 2018 Fiji doublet occurred outside the cold Tonga slab core. One event in the warm Fiji slab remnant, slab geometry complexity. The old Fiji slab leans onto the underlying Tonga slab, deforms the Tonga core, local stress rotation. Research published in Science Advances from Nature in December 2019 shows neither event was confined to the cold, brittle region. Slab temperature is critical, but local geometry dominates individual earthquakes. The deepest earthquake ever measured, May 16, 2004. Vanuatu, 735.8 kilometers, magnitude 4.2, below the 660-kilometer discontinuity. In the lower mantle, published in Deep Focus Earthquake, Wikipedia entry updated 3 weeks ago, the Tonga-Kermadec subduction produces earthquakes at greater depths than anywhere else on Earth. The Pacific Plate subducts nearly vertically, sinks rapidly, maintains cold core to extreme depths. Daily magnitude, 4 or above events occur between Fiji and New Zealand. The slab reaches depths where earthquakes should not exist, but they happen. Number 8, strike slip, transform boundaries. Plates slide past each other horizontally. No subduction, no collision, lateral motion. April 18th, 1906, San Francisco, California. Magnitude 7.9, 5:13 a.m., the San Andreas Fault ruptures, 477 kilometers from San Juan Bautista to Cape Mendocino. Slip averages 4.5 meters, maximum offset 6 meters, rupture velocity 2.7 kilometers per second. 28 seconds of violent shaking. Fires ignite. Gas lines break. Water mains rupture. 3,000 buildings destroyed. 3,000 dead. The strongest earthquake in California history until Loma Prieta, 1989. Strike-slip earthquakes have distinct signatures. Pure horizontal motion, no vertical component, right lateral or left lateral sense. The San Andreas is right lateral. Standing on one side, facing the fault, the opposite side moves to the right. Dextral motion. The Pacific Plate moves northwest at 5 centimeters per year relative to North America. Friction locks the plates. Stress accumulates for decades or centuries, then catastrophic failure. The entire stored strain releases in seconds. Elastic rebound theory proposed by Harry Fielding Reid after studying the 1906 earthquake, January 17, 1994, Northridge, California, magnitude 6.7, thrust fault, but the San Fernando Valley sits near the San Andreas system. Complex fault interactions. The earthquake occurred on a previously unknown blind thrust, no surface expression. The fault dips 45 degrees, compressional tectonics at a restraining bend. The Pacific Plate pushes into North America at an angle, transpression, both lateral motion and compression, 60 people dead, 8,500 injured, $20 billion damage. Strongest ground motion ever recorded in an urban area. Peak ground acceleration 1.8 times gravity at Tarzana, the North Anatolian Fault, Turkey. Right lateral strike slip, 1,500 kilometers long, accommodates westward escape of Anatolia, August 17, 1999. Izmit, Turkey, magnitude 7.6, 150 kilometers of rupture, 18,000 dead. The fault ruptured from east to west, propagating under major cities. November 12, 1999, Düzce, Turkey, magnitude 7.2, 90 kilometers east of Izmit, triggered by stress changes from the first earthquake, 800 dead. The earthquake sequence demonstrated fault interaction and triggered slip. One earthquake loads stress onto adjacent fault segments. Cascade failures possible. The Alpine Fault, New Zealand, right lateral oblique, accommodates relative motion between Pacific and Australian plates. 480 kilometers long. Strikes northeast-southwest through South Island. Dextral motion with vertical component. Thrust, faulting at a restraining bend. The fault ruptures on average every 300 years. Last rupture, 1717, magnitude 8 expected. Ground displacement 5 to 8 meters. The West Coast region has 2% probability of magnitude 8 or greater in next 50 years, according to GNS Science. The cities of Christchurch, Greymouth, and Queenstown sit in the rupture zone. Prepared communities install seismic monitoring. Early warning systems under development. The Denali Fault. Alaska, right lateral strike slip, 1,300 kilometers long. November 3, 2002, magnitude 7.9, 340 kilometers of rupture. Largest strike slip earthquake in North America since 1906. Slip exceeded 8 meters in places. The Trans-Alaska Pipeline crossed the fault. Engineers designed the pipeline to slide. The supports moved 5 meters horizontally, no rupture, no oil spill. The earthquake triggered landslides across interior Alaska. Glaciers fractured. The Black Rapids. Glaciers surged. Seismic waves traveled worldwide. Triggered earthquakes in California. Geysers in Yellowstone changed behavior, while water levels fluctuated in 23 states. Number 9. Normal faulting. Extension. The crust pulls apart. Hanging wall drops relative to footwall. Gravitational collapse. Some researchers term these graviquakes. Energy from gravity, not purely elastic rebound. August 24, 2016. Central Italy. Magnitude 6.2. Amatrice earthquake. 299 dead. Apennine Mountains. Normal faulting in continental crust. Extensional tectonics. The crust thins as Italy rotates counterclockwise. Ancient thrust faults reactivated as normal faults. Stress inversion. Compression changed to extension. The shallow crustal structure allows devastating shaking. The Basin and Range Province. Western United States. Entire region extends. Normal faults create basins and ranges. October 1719, 15. Pleasant Valley, Nevada. Magnitude 7.7. 59 kilometers of surface rupture. Vertical displacement 5 meters. Fault scarps visible today. October 28, 1983. Bora Peak, Idaho. Magnitude 6.9. 36 kilometers of surface rupture. 2 children killed. $36 million damage. Fault scarps up to 3 meters. Lost River Range uplifted. The East African Rift. Continental rifting. Africa splitting. Somalia plate separating from Nubian plate. Extension rate 5 millimeters per year. Normal faults throughout Ethiopia. Kenya, Tanzania. The Rift Valley drops thousands of meters. Volcanoes rise along the margins. January 9, 2005. Lake Tanganyika. Magnitude 6.8. 1,000 meters below surface. Unique location. Underwater, normal faulting in Rift Lake. No deaths but structural damage in Kalemi Democratic Republic of Congo. Graviquakes differ from elastic earthquakes. The fault volume length to depth ratio averages 3 compared to 10 to 25 for megathrusts, according to research published in Scientific Reports in July 2015. Smaller activated volumes, higher B-values and frequency magnitude distributions, lower magnitude for the largest recorded events, maximum observed graviquake around magnitude 7. The mechanical model shows intraseismic dilation followed by coseismic contraction. Extension creates space, faulting closes it. Opposite behavior from thrust faults, which show interseismic contraction and coseismic extension. The 1986 Kalamata, Greece normal fault earthquake demonstrated this with several compressional focal mechanisms during the coseismic phase. Outer rise earthquakes. Normal faulting on the oceanic plate seaward of trenches. The plate bends before subduction. Extensional stress on the outer arc. March 11, 2011, Tohoku, Japan. Magnitude 9.1. Megathrust, largest ever recorded in Japan. 40 minutes later, magnitude 7.4, outer rise, normal faulting event. The megathrust unloading triggered extension in the downgoing plate. The sequence illustrates coupled mechanics. Surface deformation from normal faulting can generate local tsunamis distinct from megathrust tsunamis. Splay faults and outer rise faults contribute to hazard complexity. The final piece, a new hazard map emerges. According to United States Geological Survey National Seismic Hazard Model updated for 2025, the central United States faces higher earthquake probability than any time in recorded history. Induced seismicity from wastewater injection, Oklahoma, Arkansas, Kansas. Regions that experienced almost no earthquakes now approach California seismicity rates. The 2014 rate was 688 magnitude 3 or greater events, down from the peak but still elevated. Models suggest continued seismicity even with injection reduction. Pore pressure diffuses slowly. It takes years to decades to dissipate. The Cascadia subduction zone remains the greatest threat to the Pacific Northwest. Magnitude 9 potential, 300 years of accumulated stress, urban areas directly above the locked zone, Seattle, Portland, Vancouver. Millions of people. The ETS events continue like clockwork, 14-month intervals. Each episode releases stress, but also transfers stress up-dip to the locked seismogenic zone. The transition zone slips regularly, but the locked zone never moves. 3 centuries of silence. Paleoseismic evidence shows the 1700 earthquake ruptured the entire 600-kilometer fault. Similar events in the 15th and 14th centuries. Rupture models, constrained by tsunami deposits in Hawaii and Japan, alternating deep and shallow megathrust slip. Maximum slip 20 to 32 meters. The next event will exceed the Sumatra 2004 earthquake and local impact. Japan learned from tsunami earthquakes. The 1896 Sanriku disaster led to tsunami stones, markers showing the high water line. Warnings carved in granite. Do not build below this point. After 1933 less preparedness, but higher awareness, the 2011 Tohoku earthquake generated a tsunami that exceeded all historical records. 19,000 dead, nuclear disaster at Fukushima. The tsunami topped seawalls designed for 7.5 meter waves. The actual waves reached 40 meters. The earthquake was magnitude 9.1. Buried strain from centuries of locked fault. The shallow megathrust ruptured to the trench. Massive seafloor uplift. Waves traveled across the entire Pacific Ocean. Deep earthquakes provide a window into mantle dynamics. The 2013 Okhotsk event showed that slabs remain coherent and seismically active to transition zone depths. This constrains mantle viscosity models. Affects understanding of plate driving forces. The Fiji doublet revealed slab geometry controls earthquake occurrence more than temperature alone. Slab fragments interact. Complex 3-dimensional stress states. Not simple down-dip compression. Slow earthquakes change hazard assessment. Episodic tremor and slip redistributes. Stress on megathrusts. The interface is not simply locked or creeping. A spectrum of slip behaviors. Transition zones between seismogenic and aseismic regions. Stress transfer from ETS to locked zones may trigger megathrust rupture. Or reduce stress if slip extends into locked zones. Geodetic networks monitor this. GPS measures millimeter-scale displacements. Networks in Cascadia, Japan, and New Zealand track every slow slip event. Catalogs build. Statistical patterns emerge. But prediction remains impossible. Too many variables. Fault heterogeneity, fluid pressure, frictional properties. Small changes produce large effects. Chaotic systems. The discovery in a borehole. Researchers drill into the San Andreas Fault at Parkfield, California. SAFOD project. San Andreas Fault Observatory at depth. 3.2 kilometers deep. Crosses the active fault zone at 2.7 kilometers. Core samples reveal fault zone composition. Not granite. Clay minerals. Serpentinite. Talc. Phyllosilicates with friction coefficients below 0.2, 1/10 of surrounding rock. The weak fault zone explains why the San Andreas slips at low stress. Plate boundary faults often contain weak minerals, hydration, alteration. The cores prove it, not theoretical, actual measurements. The fault zone is centimeters to meters wide, not kilometers. All motion concentrated in narrow zone. A lake floor in Tanzania cracks. September to 2016, the main Ethiopian rift, normal faulting. Local villagers reported ground opening over several days. Researchers investigate a dike intrusion event. Magma forced the crust apart. No eruption, but permanent deformation. Faults activated by magmatic pressure, combining volcanic and tectonic processes. The rift shows both extension from plate divergence plus magma input from mantle plume. The earthquakes reflect both sources, some purely tectonic, some dike-related. Most are hybrid. The seismic network distinguishes them by a waveform frequency content and location depth. March 20th, 2020, Salt Lake City, Utah, magnitude 5.7, Wasatch Fault, normal faulting, the largest earthquake in Utah since 1992. Downtown Salt Lake City, significant damage to historic buildings. Mormon temple loses Angel Moroni statue. Seismic waves amplified by basin sediments. Salt Lake Valley sits in a graben, soft lake bed sediments from ancient Lake Bonneville. Ground shaking amplified 2 to 3 times compared to bedrock. The same effect threatens Seattle. Puget Sound sits in a sediment-filled basin, amplification factors 5 to 10 in some areas. When the Cascadia megathrust ruptures, shaking will be catastrophic. Even at 100 kilometers from the epicenter, a coral reef rises. November 17th, 2022, Java, Indonesia, magnitude 5.6, shallow, 10 kilometers, Cianjur earthquake, 330 dead, over 1,000 injured, normal faulting, but close to cities, poor building codes, unreinforced masonry, Pancake collapse, entire villages destroyed. Contrast with California, magnitude 5.6 rarely causes deaths. Building codes matter. Seismic design saves lives. Japan requires base isolation for tall buildings, shock absorbers between foundation and structure. Buildings survive magnitude 9 with minimal damage. In developing countries, magnitude 6 kills hundreds. Reservoir-induced seismicity. December 10th, 1967. Koina, India, magnitude 6.3. 177 dead. Koina Dam. Water-filling reservoir changed stress. Pore pressure increased. Fault reactivation. The largest reservoir-induced earthquake on record. Not hydraulic fracturing. Not oil production. Just water. Same mechanism. Fluid pressure reduces effective stress. Faults that were stable become unstable. The phenomenon is well documented at dozens of large dams worldwide. Hoover Dam 3, Gorges Dam, Lake Mead, all show increased seismicity after filling. The historical record underestimates hazard. Instrumental seismology begins only in the late 19th century. Reliable global catalogs post-1900. 125 years of data. Many faults rupture every 300 to 1,000 years. Sample bias. We have not observed most major earthquakes on most faults. The paleoseismic record extends this. Trenches across faults reveal prehistoric earthquakes. Stratigraphic offsets, dated organic material, tree rings, radiocarbon, tsunami deposits, sand layers in coastal marshes. Each layer represents an ancient tsunami. Core the sediment, date the layers, build a chronology. The Cascadia record extends back 7,000 years. 20 earthquakes identified, average interval 500 years, but highly variable, shortest gap 300 years. Longest 900 years. Clustering and gaps, quasi-periodic but unpredictable. A final measurement from a satellite. INSAR, interferometric synthetic aperture radar. Measures ground deformation from space, centimeter precision over hundreds of kilometers. Compares radar images taken months apart. Phase differences reveal surface displacement. Maps the deformation field from any earthquake. The technique revolutionized earthquake science. Before INSAR, only sparse GPS networks measured deformation. Now every earthquake globally gets mapped. The slip distribution inferred from surface deformation, depth, magnitude, fault geometry, all from satellite data, no ground-based instruments needed. The 2016 Norcia, Italy earthquake, magnitude 6.6. INSAR showed complex fault interaction. Multiple faults ruptured. Slip distributed across 20-kilometer width. Not a single plane. Real faults are messy. A drill core from 2 kilometers depth in the Alpine Fault. Scientists extract rock from the fault zone. The core shows evidence of previous earthquakes, pseudo-tacholite. Friction-melted rock, flash heating during earthquake slip. Temperatures exceed 1,000 degrees Celsius for milliseconds. The melt quenches to glass, preserved as dark veins, proof of ancient seismic slip. Multiple veins, multiple earthquakes. The dating shows events every 300 years, consistent with historical records. The fault is regular, dangerous. The next rupture could happen tomorrow, or 100 years from now, but it will happen. The ground doesn't care about us. Earthquakes happen because plates move. Forces from the mantle drive everything. Thermal convection, hot rock rises, cold slabs sink. The engine runs on radioactive decay, heat from uranium, thorium, and potassium, 4.5 billion years of cooling. The Earth is still hot inside, still active. Plates will keep moving until the heat runs out, billions of years from now. Until then, earthquakes continue. We build on active faults, we live in subduction zones, we inject waste fluids where faults hide. Each choice has consequences. The Earth will shake. The question is whether we survive it